something about some work with Leonardo de Gioia, who's a graduate student at University of Campinas, Brazil. So the broad goal of the program, which I guess Monica and me and other people are part of, is to try to formulate a holographic correspondence in asymptotically flat spacetimes. So I'm going to denote AFS by asymptotically flat space. And such a spacetime, roughly speaking, can be understood as some space that relaxes to flat space away from any sources. So the setting in which we are going to work is the following. So here is the Penrose diagram for an asymptotically flat space, where there are two asymptotic regions, scribe plus and scribe minus, that are parameterized by a retarded time u, which you can think as the Minkowski time t minus some radial coordinate r, and an advanced time v that is similarly defined as t plus r. And so in this diagram, the boundary of this diamond lies at infinite radius away from the center. So lines of constant radius will look something like this. And so on the boundary, r tends to infinity. Similarly, time runs up and down. So surface of constant time is going to be something like this. But we're interested in the four-dimensional setting, this talk, and so we need to have two additional dimensions. So on this diagram, each pair of points is going to represent a two-sphere. So in particular, a cross-section of scribe plus is a two-sphere that is labeled by two angles, or a point on the celestial. Let me make sure you can see this, but we can take a cross-section of this null cone, so I'm drawing one additional dimension here, and we can put coordinates z and z bar on these spheres that are obtained by just taking the usual angles and relating them to by stereographic projections, the projection to a point on the plane. So okay, so we have a theory of gravity here inside, but as one moves far away from some region in the bulk, space-time relaxes to flat space, and so one can write down a metric, an asymptotic metric, that will just be Minkowski space, which in these coordinates that I just introduced is going to be something like this, minus du squared, minus 2 du dr, plus 2r squared, gamma z bar, dz bar, plus corrections that will be subleading in a larger expansion. So here, gamma z bar is just the metric on the sphere, and the rest should be clear. And so early on, what was realized was that this asymptotic symmetries of such spacetimes coincide with, contain the conformal group on some two-dimensional sphere. So how does that work? Let me just review. So we have maybe this order 0 kind of problem is to study the symmetries of such spacetimes near the boundary, and the way one can do that is by basically, and this was done, sorry, I should say, by Bondi, Vanderburg, Metzner, and Sachs in the 60s. And they started off with this metric, and then they chose a particular gauge in which was very convenient for the study of gravitational waves. And they then studied the conformal killing equations in this background. So basically, they looked at the set of transformations that preserve the boundary conditions in this particular setting. So for example, they looked at vector fields psi such that the change in all metric components with respect to this vector field psi was subleading to this Minkowski metric that I'm writing here. So for example, for GUU, one allows for order 1 over R corrections, while for example, GZZ, one allows for order 1 corrections, and so on and so forth. And solving this, and then what they did was to solve the set of a couple differential equations in powers of 1 over R. And what they arrived at was some vector field psi that takes the following form. I think I'm using the boards the wrong way. Yeah, okay. So psi, they found to be psi plus, this vector field psi at x squared plus was found to take the form of a function on the sphere, fzz bar d by du, plus some vector field on the sphere. And then plus subleading corrections. I'm restricting to sky, so one can jump it.
So it's fixed, or you can continue to the whole space-time arbitrarily?
No, here you can continue it to the whole
but
space-time.
But this continuation is unique, or it's like there's various number of continuations?
I think it's an open problem whether you can continue it all the way to the bulk, but this is supposed to be an exact symmetry in the sense that if you keep adding 1 over R corrections, this is supposed to continue to be a symmetry. It's not direct. It's an exact symmetry.
Local symmetry, no?
Sorry, what?
Local, no? Symmetry in the sense that...
This piece, it is a local symmetry, but then there is a whole story about some other symmetries that may exist that are a bit more non-local from a space-time point of view. But let me just focus on this part first, and let me just say, so what I wanted to point out, okay, so this piece, they are called super translations. And they are angle-dependent enhancements of translation, so they allow you to independently translate points on the sphere at infinity. So it's an infinite dimensional enhancement of just translation symmetry, which is a subgroup of Poincare. And here we have conformal symmetries. So in addition, there is, subject to certain boundary conditions, that there are additional constraints on these vector fields Y that render this piece of this vector field, so for f equal to 0, conformal killing vector field. So we have something like zy, yz is equal to 0. So this means that this piece are essentially global conformal symmetries in 2 dimensions plus their infinite dimensional Virasoro enhancements. So there is an infinite dimensional symmetry in asymptotically flat spacetimes, and one can wonder whether one can find some boundary theory with the same amount of symmetry. And this piece is a bit, maybe you think it's a bit more mysterious, but Virasoro we have seen before, and it's a symmetry of 2-dimensional conformal field theories. So it seems like a good idea to try to rewrite basically observables in this gravitational theory in terms of some observables that live on some spheres at infinity that will then transform like, which for particular choice of asymptotic states will transform like correlation functions of primary operators in a conformal field theory.
Actually, I'll ask a question before you move away from the super translations. My understanding is there are no conserved quantities associated with those super translations. Is that correct? They all identically vanish?
No, there are actually conserved quantities associated
I
with
thought there was this paper of Ashkatar, argument of Ashkatar, that showed that they were all zero.
The super translation charges, I should say, it's not going to be quite relevant for the rest of the talk, but
Oh, I realize,
this
but I
work
wanted to just ask it in passing, right? So
yeah. I'm going. Let me say. So I should say that. So these were found in the 60s. What was interesting is that recently, Andy Strominger and collaborators, they have shown that the charges associated to the super translations, for example, so you can restrict the case where y is equal to 0, and then you can write down some large gauge charges that are associated with these symmetries, and the conservation of those charges in time leads to the Weinberg leading soft graviton. So the Weinberg soft graviton theorem, which is
so the reason why I asked is this famous paper of Ashkatar, where he argues these things on states identically vanish. So this is why, but anyway, it's a talk we can talk later. Right? So,
yeah, of course, we can. I'm happy to talk later about it. Yeah, I think I know a little bit about this debate where there's symmetries of. Well, anyways, let's discuss. Yes. But they're physical. They are actually observable through the memory effect. So they definitely have non-vanishing charges that are conserved in time. So this was not realized. I mean, this was much later to the Ashtekar work, but it relies on Ashtekar's analysis. So it's not. My understanding is that it's not in tension with that work.
But are they in some sense spontaneously broken because they lived to
soft
theorems, right? Not to.
Yeah, that's right.
So in that sense, charges.
The vacuum is not invariant under the actual.
Yes, in that sense.
So in that sense, charge is not well defined, right?
Yes.
Because for spontaneously broken symmetry, charge is not acting in the space. But
yeah, that's what I thought.
The charges, the way they act on the Hilbert space is by inserting a soft graviton plus acting on the hard particle states. You can write down the action of these charges on asymptotic particle states. And this is how for example, Andy and collaborators have arrived at the soft.
Yeah, so I would say that's similar to the way that the soft charges in chiral Lagrangian, act on the state, right? They generate soft pions, right? So.
Yes.
Yeah. Okay. No, it's spontaneously.
But you wouldn't say that they don't exist, right?
well,
yeah, formally, actually, I would say they don't exist.
They don't exist, right? As operators in problem Hilbert space, but it's not problematic terminology.
Yeah.
They lead to soft theorems.
We totally agree they agree soft theorems. Yeah.
Okay. Yeah. So, anyways, yeah. So I just wanted to mention these because I wanted to introduce this dual description of gravity in asymptotically flat spacetimes in terms of some theory that lives on the sphere. So one can consider asymptotic states in this case, which asymptotic scattering states that you can take, for example, to be position eigenstates. So they will be labeled, for example, outgoing states in position space. They will be labeled by some retarded time u and some point on the sphere z and z bar. And these can be traded for momentum eigenstates that are labeled by some energy. So in the case of massless particles, I should say, they are related via Fourier transform. So here you can regard this as just a momentum eigenstate with momenta are parametrized by an energy and then some null vector, where this is a unit normal to the celestial sphere. You can write down explicitly. But none of the point is that none of these two states actually diagonalize the action of these Virasoro symmetries. So we'd like to come up with some states that instead of being, for example, these are momentum eigenstates, instead of having momentum eigenstates, we'd like to find some states that diagonalize boosts. So there is a Lorentz subgroup to the Virasoro, and we'd like to diagonalize particular generators that point towards a particular direction, towards a particular point on the sphere. And it turns out that one can achieve that by taking a Mellin transform with respect to this energy. And one arrives then at some state that is now labeled by some scaling dimension delta and some point on the sphere. And I'm dropping there can be other quantum numbers that characterize these states. such as spin, for example. So, but I'm not going to worry about that. One can generalize this construction to both spinning particles and massive asymptotic states. Okay, and then just for completeness, there is also a direct relation between these position states and these boost eigenstates, and this is just given by some integral of this form.
So this is the boost eigenstate in the direction determined by ZZ bar. That's how.
Yeah, so one can show that this is a boost eigenstate in the direction of that particular point on the sphere. So you can imagine that you're diagonalizing. So a boost in the direction of a point at the ZZ bar is essentially omega d by d omega. And you can show that omega d by d omega is diagonalized by this transformation just by an integration by parts.
So in other words, the SL2 part of these two betasaurs
Yes.
is the standard SL2 of the Lorentz group in space.
Yes. Yes, that's right.
But so how supposed to, because those states were in omega basis, that was the basis, right? And these are over complete basis or?
Yes, that's a good question. What was shown by Sabrina Pestersky and Shohan Shah is that these states, for both massive and massive particle states, they form a complete set of states, provided that this dimension omega takes a particular form. So sorry, what?
You mean the delta lies into the principal series?
Yeah, but I didn't want to say the word principal series because I don't. Okay. So it takes this form in 4 dimensions. So 1 plus I lambda, but these are not principal series representations. So I mean, they're highest weight states of dimension delta plus 1 I lambda plus I lambda. So there is a continuum of dimensions delta, and it's needed in order to get a complete set of states. But it was shown that it's sufficient it's a complete set of states for plane waves in solutions to the free equations of motion, the Klein-Gordon equations. So it's a different way of solving the same equation with another set of states, not with momentum eigenstates that are plane waves and have different energies, but a rather data set of states. I'm going to actually come back. I'm going to come back to this in a moment.
This complete set of state. I'm confused by at fixed ZZ bar or because boosts in different directions they don't commute, right? So
yes.
So
What's the normalization of different, like what is color product between D1, Z1, Z1 bar and delta ZZ bar? Right?
Yes, that's when you say it's complete set of state, you consider all different ZZ bars, or you fix ZZ bar and.
It's in the same way. I mean, you can take the overlap of the delta and the ZZ bar for delta equal to 1 plus I lambda. You can take the overlap and then you get a delta function in Z1 minus Z.
I think the question of Sergei is when you make the bracket, the inner product, whether you consider Z bar and Z bar prime or Z bar, Z bar.
Z bar and Z prime, Z bar prime. You can compute this product, and they're orthogonal in the sense that the inner product is going to be 0 away from Z equal to Z prime. It's the same as, I mean, in momentum space you get, right? They're not quite, I mean, you have to integrate against some function that you have to make wave packets. You get it's not technically normalizable, but it can be made normalizable. In the same way here, you're going to get some inner product that is going to be delta function normalizable. I should say delta function. Sorry, I'm not sure what the confusion is.
Well, the confusion is that it seems to me that boosts related to different values of ZZ bars, they don't commute, right? Boost in that direction, they can. So it's a bit confusion to have a basis.
No, but this is boosts. But
okay. So they
it's
do not compute, so I cannot diagonalize them simultaneously.
You do it on a single particle. For each single particle, you actually diagonalize a different boost, but a boost along the direction that that particle is traveling. Which you're allowed to do. you can work with single particles, right? The multi-particle state is just a direct product of single particle states. You can work with single particles, and each one can be taken in any.
So for single particle state, if I really consider single space of a single particle, that corresponds to a particular value of the bar, right?
Yes.
And then different particles, they're labeled by basically different values of the bars, which correspond to.
Okay, so given this set of asymptotic states, one can express the S matrix as follows. So in this new basis, this object is related via this map to the usual momentum space scattering amplitude that one computes in quantum field theory by some Mellon transform over all these external particle states. So. And here we just have say some momentum items. And okay, and conveniently one can also just, since now this object is labeled by points on some sphere and some dimensions delta, this new observable, which is just simply the same old S matrix, but expressed in a different basis of asymptotic states, has the same properties, or can be rewritten as some correlation function of some operators that are inserted at points on the celestial sphere. Right,
Actually, question.
Yes.
You said it is observable like the S matrix, but the gravitational S matrix has infrared divergences. Is this an infrared safe observable?
Yes, this is a good question. So you can. So I'm not going to focus on that problem in this talk, but you can make an infrared safe observable in the celestial CFD by choosing these asymptotic states to be particular kinds of dressed states that involve these coherent states. From a bulk point of view, they would be related to the construction of AdS and Schlisch, where they used coherent states of, for example, soft gravitons to eliminate
So this is a block-node-stick like construction. So this is like a block-node-stick kind of construction. Block-node-stick solves this problem for QED.
I mean, you have to. There are two ways to solve the problem, right? You can either compute inclusive cross sections, or you can compute dressed scattering amplitudes.
Yes.
And here, I'm just going to take the point of view that I'm just going to focus on the scattering amplitudes. So the level of the scattering amplitudes to make this you may say that the scattering amplitude is never an observable, but only cross sections are. But you can always build cross sections from scattering amplitudes at the end of the day.
Yeah, so, I've just been careful because, at intermediate stages that there might be, these things might be ill-defined, and the
yes,
question
I
about,
agree, and it is a problem that has been partially solved, but I would say it's not been completely solved in gravity. So what we know is that there is a way in which one can write down infrared finite observables in gravity by inserting, in addition to these operators, some vertex operators on the celestial sphere that are these analogs of these Faddeev-Fuller states.
Okay.
And when you define in states, so those are kind of analog of what we define out states, but on the square minus, right? But for that, one needs to take that vector field and kind of continue back to square minus, right?
Oh, I glossed over that. Yeah, I agree with you. Yes, there are two spheres. You're worried that there are two spheres really, and how does one go from square minus to square plus? And this has to do with this charge conservation law in time that can be obtained by imposing a matching condition at I0. So not, let me just explain that. Yes, so you can, the charges associated with super translations, they are defined at scri plus minus and scri minus plus. They live here, and a priori they are two independent objects. But to arrive at this conservation law associated, well, to arrive at the conservation law, one has to impose a relationship between these charges. And it turns out that the right thing to do is to actually impose an antipodal matching condition across I0. So you can, for example, later on, people have shown that you can blow up I0 with some zeta slices, and then there is some matching condition along those slices that relates the value of the charge here to the value of the charge there, and right. And once you have matching, so once you have imposed this matching condition, you can then extend, or even before if you want. But the integrals here, they can be extended to an integral over full scri minus and over full scri plus by the constraint equation, so by the UU component of Einstein's equations. And that actually will give you a relationship. So together with the matching condition, you will get the relationship between the charge defined on a Cauchy slice that is taken to the scri minus and the charge on a Cauchy slice that is taken to the scri plus. And these two charges have to be equal, and so this is the statement of charge conservation.
So in this matching terms of this vector field is basically turns U into V, and then that does something to ZZ bars, right?
Yes, so Z prime would be -1 over Z bar. So it's just an antipodal, it's an antipodal matching condition that one is used. And in that sense, the sphere, I mean, you can do the same for scri plus and scri minus independently, but by the matching condition, you can put all of your asymptotic states on the same sphere. Yeah, thanks. So okay, so I'm going really slowly, but yeah, so we have these are called celestial amplitudes. And you can study the symmetries that act on these amplitudes, and okay, by construction, these will transform as correlation functions of primary operators in a two-dimensional conformal field theory. So these guys diagonalize these boost generators that correspond to scaling operators or correlation operators in the two-dimensional conformal field theory. So this is fine, but then there is an interesting action, for example, of translations on these celestial amplitudes. So one arrives at additional relations that have to be obeyed in basically Poincare invariant theories. So for example, if you study the action of translations, you find that, so translations, just let me write it down, translations will act by shifting the dimensions delta of these operators by 1. And so momentum conservation essentially would impose a constraint, like a relationship between celestial amplitudes involving operators of shifted dimensions. So according to this rule. Then there is this whole story about soft theorems and so on and so forth. But so I'm happy to chat about this later, but since I wanted to start actually to discuss
what is Q hat there?
Yes, I'm calling this omega Q hat. It's a non-vector that is thank you for asking. So there is a rich symmetry structure, and these celestial amplitudes are constrained by symmetries. And most of the yes.
And that shifts you away from the basis that you started with.
Yes, but really, if you think about the things one should care about, are really just expectation values of all these operators. So when you just consider those, then it's the fact that operators have shifted dimensions is not this. You may wonder about the tension between that and that.
Yes.
But I'm saying that the thing that matters is the thing that matters would be the expectation value of the translation operator in some states of definite delta. And so if you think about that, one can.
I'm just asking whether this is the ordinance you get from p hat
it's going to be somewhere that you can interpret in terms of between the original scattering amplitude.
At the level of the original scattering amplitude, this is just going to be the fact that the amplitudes are distributional, so they're multiplied by momentum conserving delta function.
But since it becomes more mysterious when you go to this,
I
go to
agree
the
with
bull
you.
spaces.
I agree with you. It's because, I mean, when you do this map, you actually, sorry, this is the full amplitude including the momentum conserving delta function. So it's the momentum, the invariant amplitude under translations. And so that delta function has to be somehow, the fact that you started off with an amplitude that was distributional and it had this momentum conserving delta function in it, has to be reflected in the spectral amplitude.
That's coming from some change of this contour in the inverse magnetic transform.
You mean that? Yes. So if you want, sorry. So what? Sorry, what is exactly?
Because naively that shifts you away from the deltas, the spectrum of delta that you use to define this map, right?
Yes, but if you think about how you would write the state in terms of an inverse Mellin transform, there is a freedom in the contour. In the contour. So yes. But okay, still I agree with you that, I mean, there is a lot of these shift symmetries also associated with the soft theorems, and it's interesting to study their, like, to what extent they constrain slash amplitude. Okay, but what I want to talk about today is
But they map primaries into primaries.
translations.
No, I mean, the translation, yes. You just map primaries to primaries with different dimension or non-primaries?
They map primaries. Yes, they.
So it's not like in a spectral flow or nothing like that.
Yeah, you should do it.
They will be different representations. They're not in the same. They will be mapped into different highest weight states with a different highest weight dimension that is given by delta plus 1. So they won't be in the same multiplet of the conformal group. Yes, these states that are obtained by acting with these translations. Okay, so yeah, so far I have just described how to get from a known momentum space carrying amplitude to these celestial observables, but one may be interested in seeing whether one may have a construction of these celestial CFDs that didn't rely on performing this map. And one question that one can ask is whether one can say something about these observables, about celestial amplitudes from the standard AdS CFD correspondence. So I guess roughly the question I would like to ask is whether one can get this asymptotically flat space celestial CFD correspondence from AdS CFD. And there are two reasons to believe that that should be the case, and or really one we can be combined into one reason, namely the fact that the flat space S matrix is somewhat known to be obtained from a flat space limit of AdS CFD correlators. And let me just sketch some previous work on that. So one of these ways of obtaining momentum space carrying amplitudes from a flat space limit of AdS CFD relies on the HKLL construction. So this is a map that relates bulk fields in ADX to boundary operators. So what one finds, so typically, okay, one would get a relationship between some bulk field in ADS as some integral over, so say we are in ADS V plus 1, so this would be an integral over the boundary CFD variables, and we have some kernel here, this HKLL kernel that depends on some bulk point in ADS and on some boundary point. So you have something like that. But what happens to be the case is that as one takes the limit, so one can restore powers of the AdS radius by dimensional analysis and then take the radius r to infinity. in which case this integral turns out to become very simple, and it's roughly speaking something like this. And now the idea is that now we see that there is now an omega dependence, so this would be kept fixed and would correspond to the energy of a mode of this field in AdS, and this is just an operator on the boundary, and this tau is just the global time in the boundary d-dimensional conformal field theory. So basically what this gives us is, as r goes to infinity, one finds some relationship between now flat space. Also in this limit, right, what happens is that one zooms into some flat region of AdS, and one finds a relationship between now flat space field, free field modes, and operators in some boundary conformal field theory. And in particular, at large R, we see that this operator localizes at some particular tau here, depending on where you choose the origin in your spacetime to be. So depending on what region you choose to focus on, you're going to be localizing the operator on some slice that is null separated from this region in the middle. So something like this happens. And here is tau. This is the AdS radius. Right. So this is one way, and in this way one arrives at momentum space modes, right? So momentum space carrying amplitudes will be recovered from conformal correlation functions via this prescription. And of course you can say that, and then I can just take this and go through that procedure, and then we can arrive at celestial amplitudes. And then there is another sort of complementary, but I guess equivalent approach that relies on Mellin correlators in CFT. Sorry, I should say that this dates back to Kolchinsky and Saskin. And this story about Mellin correlators, I guess, dates back to Penetanes. And here the idea is a little different. So here one starts with, again, sorry, I should just insist on notation. One starts with correlation functions in some boundary conformal field theory, and rewrites this as an inverse Mellin transform with respect to some dual variables to the conformal invariance on which this correlation function depends on. This is going to be inversely proportional to some delta ij, and then one has some Mellin transform with respect to these conformal invariants that you're denoting by m, and then there are some normalization factors, essentially gamma delta ij, and then we have the conformal invariants. So this is just a Mellin transform with respect to these xij squared. But what was observed by Penetanes is that actually in the limit as r goes to infinity, and also these dimensions delta ij go to infinity, this dual correlator has the same behavior as a momentum space, flat space carrying amplitude. So more recently, in some interesting work, let me put it here, the relationship between these two prescriptions has been sort of studied and reviewed. So there is a way to sort of unify these two descriptions, but in either case, right, what we arrive at is a flat space momentum space carrying amplitude rather than a celestial amplitude. So what one can ask is whether there is a more direct way of obtaining celestial amplitudes instead from this prescription, just because the celestial amplitudes naturally diagonalize some subgroup of the higher dimensional conformal group in this case. So can we find some way to arrive directly at celestial amplitudes? So just again to draw some diagram. So these two can be summarized by, for example, for 4-dimensional AdS, but it also works in higher dimensions. One has some correlation function in some 3-dimensional conformal field theory, And there's two ways, either this HTLL or this conformal, this Mellon transform with respect to conformal invariance. And in this way, one arrives at some scattering amplitude, typically in momentum space, as one takes R to infinity. But here we know that as we take some, if we were to take Mellon transforms with respect to the external energies, we would be arriving at celestial amplitudes. And basically the question I'm trying to ask is how to directly get, it seems like more natural to directly get from CFT3 correlation functions to celestial amplitudes on the sphere. So yeah, so to see how this works, let me just say one more thing about another way to, let me just discuss another way to obtaining celestial amplitudes in 2 dimensions. So of course one can apply the prescription that I said before, but one can also start.
Sorry, just
Yes.
to be sure. So on this side of the story, the corresponding particles in the bulk doesn't need to be massless, right?
Sorry, yes, there is a distinction here. So here, typically the particles are taken to be massless.
Oh, okay.
But here we're going to see that it's natural to get actually massless amplitudes from this prescription. So yeah, so let me just say one more thing, namely that a momentum space scattering amplitude on endpoints can be obtained from a time order correlation function in the bulk by integrating against plane waves. So basically there is a formula like this.
Sorry, just to understand, from the Wald point of view, having massless particles in AdS is qualitatively different because they can't touch the boundary.
Yes.
So you have these fixed points there,
yes.
and then you can take the limit of being a null surface.
Yes, so I'm going to focus on the massless case. This was just to review what people have done before. I think it's not so known how to do the massless case in these pictures. Yeah. So yeah, this was just motivation, and I'm going to just present an independent way of arriving at celestial amplitudes of massless particles from a similar flat space limit prescription. So let me just say that, okay, so this this is just the definition of a momentum space scattering amplitude. This is a time order correlation function. These are plane waves. But what I want to emphasize is that by the fact that these are chosen to be plane waves is kind of, well, it's because one typically wants to work with 3 particle states that solve, this usual picture of Poincaré representations where one starts with momentum eigenstates. So it's natural to take the plane waves in this case, but given the story that I presented before, it seems more natural to take these can be arbitrary wave packets, right? And one can start off instead with taking these asymptotic wave functions to be conformal, so-called conformal primary wave functions instead. So if one replaces the plane waves by conformal primary wave functions, and these take the form, this following form. So they're still functions of these null momenta and of bulk points. There's something like this. Then in that case, one obtains celestial amplitudes. And you may say that this is more complicated than this other prescription that I gave because it involves many integrals over these these bulk points x. Sorry, I should say that these are time order correlation functions that are amputated, so in the bulk. But actually, the two prescriptions are equivalent. Yeah, so I don't have to erase that. So to see that they are equivalent, one can simply notice that if we were to just instead just take a Mellin transform of these plane waves according to that prescription, then we would essentially find something proportional to these conformal primary wave functions. So we have x, and here p is essentially omega to have. Right? So we see that if I just take a Mellin transform of this formula, the Mellin transform will transform the plane waves precisely into these conformal primary wave functions. And so we sort of have proven this claim that celestial amplitudes are just given by this formula, but where these asymptotic plane waves are replaced by conformal primary wave functions. Okay, so that now allows us to sort of, this formula is going to be useful to establish this relation that we are looking for between CFT3 correlation functions and celestial amplitudes. So before doing that, let me just also describe AdS again for a second. So I'm just going to work in Lorentzian AdS. So we have the Lorentzian cylinder that is parametrized by some global time tau and some angular coordinates omega, and the bulk AdS, the bulk coordinate rho. So in the bulk here we have, I'm going to focus on AdS4, and then we have some CFT3 on the boundary. And yeah, it's convenient to use this embedding space formalism, but maybe due to lack of time, I'm not going to describe that. So hopefully, please ask any questions if the setup here is not clear. So what I'm doing is to just put some coordinates, parameterize AdS4 with particular coordinates, rho, tau, and these angular coordinates omega, and then one can essentially express all of these observables in this context using certain integrals over these coordinates. Yes. So, for example, if we want to calculate, and I should say another thing, namely the fact, so it's known that CFT3 correlators are related, can be obtained by summing over AdS Witten diagrams. Involving various channels in a similar way as one would do in flat space. So a Witten diagram is basically consists of a process where now I'm representing the boundary by a circle, and one has, for example, at the tree level, you have some diagrams of this form where the boundary points, let me denote them by one. Sorry, this P is not, annotation is that this P is not the same P as here. Yes, I'm just labeling boundary points here. It's an embedding space vector if you want. So P3 and P4, and then there are points in the bulk, and again these are points in AdS, not in flat space. So say here x1 and x2, and this diagram, the corresponding AdS Witten diagram in this case, is going to be constructed by applying Feynman rules. So here in particular, what one has to do is to integrate again some amputated correlator in bulk AdS, so some bulk to bulk propagator. That will depend on these points x1 and x2. And we also need to integrate against some bulk to boundary propagators. That will be labeled by P1, x1. Okay, so there's going to be, so here in this particular example, we have one bulk to bulk propagator and 4 bulk to boundary propagators. Okay, so in this way of writing things, one can then study what happens in the flat space limit. So I'm going to define the flat space limit, or actually I'm going to define, but the flat space limit of an observable in that form is defined as the limit in which one sets this global time coordinate tau to be tau divided by r, and this rho coordinate to be little r divided by big R. And one takes r to infinity for fixed t and rho. And in particular, in these global AdS coordinates, if one takes this limit, one can show that the AdS metric just reduces to the flat space Minkowski metric. So you'd want to apply this to such a Witten diagram, but given the intuition, this won't be sufficient. So if one just arbitrarily considers a correlation function.
I'm confused. I thought it was going to be the other way around. So it means that I fix the time on the celestial. So this is not the tau. The t is the one on Minkowski space, right?
Yes.
And then I take the limit in which the separation in the boundary of AdS tends to 0. Right? That's what I'm doing because L goes to infinity.
This is like E in AdS.
T and R, I think you mean, right? Not rho.
You should think about, so these are
I mean,
AdS coordinates.
Tau is the difference between the three starting points of the.
No.
Okay.
No, sorry, tau, sorry. Tau, I
because
should
before
say,
it was a drawing. There.
I'm sorry.
That tau there.
No, sorry, I didn't mean the distance. Tau, it
Okay.
only has one way.
So
I just meant it
what
to
is
be.
this tau?
Tau is just a global AdS coordinate. So for
Okay,
example,
no, I
if you
thought
have-
it was a separation. In that
No,
coordinate.
sorry. Tau is not a separation. Tau is, so you would have to do this. You would have to do, so for example, a correlation function on the boundary will be labeled by a collection of taus, rho equal to pi over 2,
Yeah.
and collection of points on these three.
So it's just trying to understand how to picture the limit in which the boundary will become somehow non-infinity, right?
Yes, I'm going to say that now. It's not quite the boundary though.
No?
The boundary will sort of become null infinity. I mean, but the prescription is going to be okay, the usual flat space limit, you'd have to do this, but you would see that, I mean, just naively by counting the dimensions, right? In this case, it's not going to be enough to just apply this limit, because a correlation function in a CFT3, right, will depend on all the taus corresponding to the operator insertions, as well as the angular coordinates, right? So that's going to give you an object that is not going to live on a sphere. But what one can do instead, motivated by this HKLL prescription, where the operators actually localize on some slices that are null separated through the bulk, one can, what one can try is to actually start by localizing, so localizing the boundary operators. To some tau slices separated by pi. So here we would have, so we can consider this slice, and then we can consider another slice here, and the separation between the two slices now is going to be some delta tau that is equal to pi. But this is not equal to 0, right? So we can consider a particular kinematic configuration for these operators on the boundary, and then we can take this flat space limit, and the punchline, yes.
Just to clarify, are you fixing tau or are you fixing t? We wrote there for fixed t and rho. So you said r to infinity for fixed t and rho.
Yeah, no, for fixed t and r.
So you mean r there, okay.
Yeah, so for, oh, sorry. Thank you. Sorry about that. For fixed t and r. But actually, for like the boundary observables will just depend on, they will just depend on tau and the angular variables, right? One integrates over the rho anyways in the bulk. Okay, so let's start with, you can start with this physically motivated prescription, where in this particular configuration, right, these bulk lines will meet at some point that correspond to some flat space region. And the punchline is that actually in this limit and for this particular configuration, these AdS Witten diagrams will actually reduce to celestial amplitudes. And to see that, well, it's quite simple. One can just analyze the constituents of this AdS formula that I've written down before. And the main point is that this bulk to boundary. Okay, let me write more. Bulk to boundary propagators actually take this explicit form. So again, these P and these X's are embedding space vectors. You should always regard them as embedding space vectors. So you have an AdS 4.
Sorry for being annoying, but
no, yes.
Suppose you do it in one dimension less, in which you already have a Virasoro action on the boundary of AdS. And then you take all this limit, because in principle you could take the same limit, right?
Yes.
You would say that this Virasoro becomes your super translation.
You want to be in
one dimension
AdS
less,
3
yeah.
and you want to have some
Because in flat space.
Yes, you could do that. And then you would localize things on.
But in one dimension less, celestial holography has no two Virasoros, only has one, right? So that's.
Yes.
But in AdS CFT.
But sorry, celestial in one dimension lower, you just.
One Virasoro.
Yes, you have one Virasoro.
But in one dimension less, in AdS CFT, AdS 3 CFT 2, you have two Virasoros. So
yes.
Which is the Virasoro that becomes your Virasoro?
Yeah, that is a good question. Actually, with Leonardo, we are studying similar question right now, but here it's just about, it's not, yeah, it's a good question. Like how do the symmetries of the boundary...
Because here it seems you have some emergence of symmetry because it becomes dimension, but in that case you are losing symmetry.
Yeah, that's a good point, and I haven't thought about that lower dimensional case actually, but you're losing it because I think you're restricting to a particular circle, if you want, in this two-dimensional theory. So,
because here you are winning a lot, right? Because you start from a finite dimensional conformal group and you get a BMS.
Yes,
But I think in 3D people understood how to get BMS 3 from
yes, some kind of
some contraction.
vector contraction.
Right.
Yes,
that's right.
Belgium guys.
Yeah.
Yes, okay. So just to sketch how this works, so here's your question.
But in 4D it's a bit mysterious.
Yeah,
it really comes from nowhere, this BMS.
Yeah.
Yes, but that question is work in progress actually. So we're still thinking. Yes, but it will. We believe that it will work. So yeah. So this expands. So what one has to do is to take this propagator. So again, these P and these X's, they are embedding space vectors, so they will have 5 components, right? So what one can do is to see how this what this goes to as one takes R to infinity and this P corresponding to some, say, tau equal to either plus or minus tau over 2, pi over 2. And yeah, you can, since I'm actually over time already, I'm not going to write down the expression, but the point is that you can actually explicitly show that this precisely becomes this conformal primary wave function that I wrote down before. So, and in particular, for tau plus pi over 2, this will be an outgoing one, and for tau minus pi over 2, it's going to be an incoming one. And importantly, one also has, in order to get Lorentz invariant answer at the end of the day, one has to antipodally, these two spheres that are separated by pi have to be antipodally matched.
It will be corresponding to realizing the flat limit,
Yes.
the I0 condition, the condition at the space like infinity.
In order to end up with an answer that is actually Lorentz invariant, so like invariant under two-dimensional global conformal symmetry.
No, yes,
Yes.
My question is very nice. This antipodal condition that you put in AdS maps to the standard antipodal.
That is a good question. I don't like it hasn't been really shown, but what like okay, Laurent, for example, Fidel has he has suggested, for example, studying the like for example studying solutions to equations in AdS and trying to see whether like such a matching condition could arise. So for example, in the usual flat space case, one approaches the boundary from different light cones, and here you can try to see whether something similar happens to actually derive that matching condition if you want. But we haven't done that. Here we just observe that if you do this, then we end up with celestial amplitudes. So anyways, so the main observation is that this bulk-to-boundary propagator in AdS reduces to a conformal primary wave function, and together with the fact that the bulk-to-bulk propagators will also reduce to Feynman propagators subject to certain boundary conditions, and also these integrals will reduce to flat space integrals in this limit. And so putting everything together, so yeah, and putting everything together, provided that there are no subtleties. So this is also something that we'd like to understand better. If there are no subtleties related to these integrals over the full bulk AdS, it looks like the AdS Witten diagrams actually reduce naturally to celestial amplitudes in this particular limit. So this is so this was one of the results, and one can do this in an example, but since I'm out of time, let me just say in words what one can study, for example. So one can look at some AdS amplitudes, and an interesting example that, for example, has not been studied before in flat space is the propagation of a particle in a shockwave background. So say you have some shock and you have some particle. It's known that as it crosses the shock, it's going to acquire some phase shift with respect to, so this is x minus, this is x plus. So there's going to be some delta x minus here. And so one can compute the 2-point function in this shockwave background. And one can also compute the associated celestial amplitude. So this has not really been studied before, but you get to an answer that actually turns out to be very, very similar to an answer that Panedones, Costa, and Cornalba obtained in the mid-2000s on propagation on a similar problem, but in AdS. So the answer one gets in the celestial CFT is very similar to the answer in AdS, and indeed, when one runs through this prescription that I derived here, one is able to actually conclude that the AdS 2-point function actually reduces to the celestial amplitudes directly in that limit. And there's things that one can try to do later and relate this to iconal amplitudes and so on and so forth. But yeah, I'm not really going to have time to say more about that. But yeah, so I'm happy to, and there's many future directions that one can do. Of course, this is exciting because it may say, well, one natural question is to try to see how the symmetries of the celestial CFT would arise from this flat space limit, and this is work in progress with Leonardo, but then it would also be interesting to study other problems related to infrared divergences, for example, since there was a question about that. So all of this is related to the Weinberg. So there is this whole story about infrared divergences, but these exponentiated divergences actually have a real part and an imaginary part, and all of this is actually related to this imaginary part that in 4 dimension also leads to a divergence. It is also divergent, and it would be very interesting to understand better, for example, how to compute that just purely from a CFT perspective, celestial CFT perspective, if you want. And more generally, it would be interesting to, for example, study some known holographic correspondences. So, for example, such as these ABGM models of string theories in say AdS 4 plus 7 and see if one, in that particular case, what one would get out using this prescription. So presumably one will get something that looks like a celestial CFT with certain properties. The bulk is going to maybe weird, but it will be interesting to see what one gets. So thank you very much.
Questions?
Good question. So physically, how would you characterize this kind of 2D subsector of the three-dimensional CFT?
What do you mean?
Which are connected by this flat space limit of the holographic dual.
By physically, you mean
So,
like
so,
what is?
so if you go through the AdS CFT and then the flat space limit,
Yes.
you have constructed some kind of 2D sector of the three-dimensional CFT with the
Yes.
holographic dual.
Yeah, that's right.
So can you kind of characterize that directly at the level of three-dimensional CFT? What is the physical?
Yes, that is what we're trying to do now. So just starting from a purely CFT3, just conform a field here in 3 dimensions or actually higher dimensions. The first question one can ask is what happens to the symmetries and the global symmetries in CFT3 in this limit, then you can actually show. But again, hopefully the paper will be out soon. But what one can show is that you get out this DMS symmetries just purely by analyzing the CFT3, and then you can ask how do, for example, soft theorems in the bulk arise from this prescription, and you can actually also answer this question at the leading and sub-leading orders in gravity and the leading order in QED.
So do you, like for the very basic observable, like associated with symmetry, like the center charge for the Raclariu, how is that information contained in a three-dimensional
The central
CFT
charge,
data?
I think, is going to be washed out. I mean, there's going to be some central charge of the CFT, but it's in this flat space limit, it's going to become infinite, presumably, and so somehow
The Raclariu center charge for the celestial CFT is going to be infinite?
we are not as far. Yeah, because the central charge actually scales with the AdS radius.
You think 3D central charge becomes infinite or 2D central?
In the scaling limit, I think it will
3D
become
central
infinite.
charge, right? Like central charge of the
It's
3D
close to
Yes,
the
the
CFT.
3D
But I think he's asking about the Raclariu central charge of 2D.
Yeah, but how would you extract
but so it's
the central charge?
Sorry, it's infinite in the sense that the scale is n, right?
Yes, exactly.
Yeah, but it's some precise.
I don't know how
So
to
you're saying the Raclariu
extract-
center charge will scale?
Yeah.
It will
You're
scale the
asking
same way
how
as the
right.
three-dimensional center
The
charge?
original central charge of the original CFT that you start off with should be contained in this, like that information should be contained in the dimensions, and it would be very interesting to understand how to extract that, because currently there's been some studies on just celestial CFT where like some people are saying that C should be 0 and some others are saying that C should be
that's why I was
infinite.
asking this question, yes.
Right, but there should be some info. I agree. From this perspective,
Yes.
yeah, there should be some finite answer that somehow one should see, but
Well,
I don't,
you
the
don't-
answer to
you
this
don't-
question, I don't know.
In CFT3, you don't have any central charge to start.
So this is I'm talking about the stress tensor 2-point function.
Okay.
So that defines this
From that-
CT,
from that.
which is analogous center charge in
Yes.
3 dimensions,
Yes.
which
but-
also controls the Newton's constant for rapid flow.
Yeah, I think that would be an interesting question, but we have like that we have not there yet, so we haven't studied that yet. But I agree.
So you mentioned when taking the flat space limit, you also see the subleading symmetries of gravity, so like the rotation.
We think so, but I'm not very confident yet about the answer since it's not. I mean, we think so.
I'm only asking because rotation usually comes with its own added complications. It's
Yeah,
not probably like flat space.
I agree, and we were a bit confused about that because, like here, you can regard this thing that we are doing as series of contractions from formal algebra to Poincaré to DMS, like whatever. But in those contractions, you actually never get the Raclariu, but somehow here, maybe you're doing something wrong and it shouldn't be there. I'm not sure, but it seems like so
it's
far
not
we
like
seem
trivial.
to-
It's really
It's
those
not-
have complications that.
It seems like it does pop out in this limit, but in particular for 3D CFTs, not for higher. If you start with a higher dimensional CFT, you're not going to get the Raclariu from this prescription. Well, not from the like extending this to study symmetries and so on and so forth. It's a special thing about 3D CFTs. But again, don't since it may be completely wrong, so I'm not in this report. So.
More questions? If no, let's thank Anna once again. So and we will have seminar dinner at 5:30. If you're interested, please tell me.
Stop the recording.